All right, hi everyone, welcome back. Hope you had a nice spring break. Today we are starting chapter 10, so we are on 10.1 notes. This is right triangle applications. So first we have an area of a triangle. So this will work for any area of a triangle. It does not need to be a right triangle. So we have 1/2 side A times side B times the sine of theta. The important part to note here is that this must be a side angle side. So must be side angle side triangle. So for example, if we have side A, then we have theta is in the middle, that's our angle, and then side B right there. So it would not work if we were using an angle over here and we had sides A and B. Okay, so you have to use two sides with an angle in the middle. So here we have in number 1, this triangle ABC. We want to find BC and AB using our 45, 45, 90 triangles. So if you think back to geometry, when we have a 45, 45, 90 triangle, our sides are in a ratio of x, x, and x root 2. So across from our 45 angle is 9. So I would have 9, 9, 9 root 2 would be my hypotenuse. So BC would go ahead and be 9 centimeters. And then AB would be 9 root 2 centimeters. Okay, in number 2, we want to again find BC and AB, but this time using our right triangle trigonometry. So this is where we want to bring back SOHCAHTOA. So the angle that I am given is 45. So across from there would be my opposite side. We have our hypotenuse and then our adjacent side. So let's first find BC. So BC is going to use our opposite side and adjacent. So that is going to be tangent. So I would have tangent of 45 degrees is equal to the opposite side, which is 9, over the adjacent side, which is what we're trying to find. Now, tangent of 45 degrees, that's just going to be 1. So 1 equals 9 over x. Solve for x, and x equals 9. So BC equals 9, which does match up with what we did in part 1. Okay, now we can go ahead and find AB. So AB is going to use my opposite side and the hypotenuse. So that is going to be sine. So AB is going to be sine of 45 degrees is equal to the opposite side, 9, over the hypotenuse, x. Okay, well, sine of 45 degrees is just root 2 over 2. So if we just cross multiply, I would have x root 2 is equal to 18. Okay, so x is equal to 18 over the square root of 2. We just have to rationalize the denominator here. So x is equal to 18 root 2 over 2. So then AB is equal to 9 root 2 centimeters, which once again does match with part 1. Number 3, we have a ladder. It's 18 feet long, and the angle of inclination is 60 degrees. So that is going to be our angle down here. And this is going to be a right angle. So my last remaining angle is 30 degrees. So we want to find how high up the building does the ladder reach. I feel like that's worded oddly. But okay, we want to find x. We want to find the height. Okay, so again, if you recall from geometry, we have a special right triangle, 30, 60, 90. The ratio of the sides is x, x root 3, and 2x. Okay, we know that the ladder is 18 feet long. So that is across from my right angle. So 2x is going to be 18. So then I can find out that x is 9, and then x root 3 would be 9 root 3. So we want to find the wall. The wall is across from the 60-degree angle. So the wall would be 9 root 3 feet. Okay, for a word problem, that doesn't really make too much sense if we have a radical in there. So if you type that into your calculator and round it to the nearest tenth, you would have approximately 15.6 feet. So the ladder is about 15.6 feet, not the ladder, the wall is about 15.6 feet high. Okay, or that's how high the ladder touches the wall. All right, then we want to find the distance from the base of the ladder to the base of the building. So the base of the ladder to the base of the building, let's call that Y. Okay, and that is across from the 30-degree angle. So without doing anything, if we just look, that would be our X side, and we already solved for that in part A. So 9 feet. Okay, so the distance from the base of the ladder to the base of the building would be 9 feet. Okay, and number 4, we're trying to find the distance across the lake to the nearest meter. So here we have one part across, we're trying to find from point A to point B, and that is labeled as X. So here we want to bring back SOHCAHTOA again. And so our angle is 40 degrees, and we have our hypotenuse, and we have our adjacent side. So that would go with cosine. So we have cosine of 40 degrees is equal to 400 divided by x. When we solve for x, we end up having 400 divided by cosine 40 degrees. So this we're going to have to type right into our calculator. Make sure that you change your mode to be degrees instead of radians. So when you enter this into your calculator, we should get that x is approximately, if we're rounding to the nearest meter, 522 meters. Okay. And number 5, we have theta that is equal to 39.4 degrees. We have x is equal to 43 feet. And then h is an altitude. So we are going to end up having some right triangles here. So we want to find the base of the entire triangle to the nearest tenth. So I am looking for this entire base. Okay. So if we label just this section, this one right triangle, if we label that base as x and we're using theta, then I am going to have my adjacent side and my hypotenuse. So I can have cosine of 39.4 degrees is equal to the adjacent side x divided by 43. So when we solve for x, we have 43 times cosine of 39.4 degrees is equal to x. So x ends up equaling 33.2 feet. Okay, now if I want to find the base, and I know that this is an isosceles triangle because both sides are x and we have an altitude, so each right triangle is going to have the same base. So the entire base of the triangle is just going to be 2 times 33.2, which is equal to 66.4 feet. So our entire base is 66.4. Okay, in part B, we want to find the area of the triangle to the nearest 10th degree. So if we're looking at what is given to us, we have our angle and we have two sides, and it is in the order of angle, side, angle. So we can use the area of a triangle formula that was on the front. So the area is equal to 1/2 side A times side B times sine of theta. So this would be 1/2 43 times 66.4 times sine of 39.4 degrees. Enter that all into your calculator and we get approximately 906.1 feet squared. And number 6, the radius of the circle is 1 meter. The inscribed hexagon is regular. Find the area of the shaded region. So what we can do here is when we have a regular hexagon, I know that we can end up having 6 equilateral triangles. So I'm just going to draw them in here so it's a little more pronounced. And if we have equilateral triangles, then we know that all of our angles are going to be 60 degrees. Okay, I also know that the radius is 1 meter. So I'm going to have 1 and 1. So I can go ahead and find the area of an individual triangle and then just multiply that by the shaded triangles, which would be 4. So here I have the area of one of the equilateral triangles is 1/2 1 times sine of 60 degrees. So we end up having 1/2 times root 3 over 2. So the area is equal to root 3 over 4. Okay, and then we have 4 shaded equilateral triangles. So the area of the shaded region would just be 4 times the square root of 3 over 4, which is just going to be square root 3 meters squared. Or if we type this into our calculator, that's approximately 1.73 meters squared.